Good afternoon, everybody. Welcome to the ESRF webinar. We shall start in a few minutes from now. We are still waiting for a few more people to join us. So stay tuned. We start in a few minutes from now. So I think we have already many participants and we should start not to run late. So my name is Patrick Bruno. I'm a theoretical physicist at ESRF. And it's my pleasure to welcome you to today's ESRF webinar. The ESRF webinar is a series of events that we started just before the summer break due to the pandemic situation worldwide. And as the situation remains very complicated everywhere, we don't run any traditional seminar, and we will continue this series of webinar at least until the end of the year. So a few technical, practical information. So you are likely to be viewing this on Zoom. This can be, in principle, also seen on YouTube. Maybe we have a problem right now, but anyhow, the talk will be available on YouTube for replay on the ESRF YouTube channel. Also, I would like to make the announcement that in a week exactly, at the same time, there will be the joint ESRF ILL colloquium on the topic of exoplanets, discovering new worlds, when the speaker will be Professor Anne-Marie Lagrange from Institut de Planetologie and Astrophysics de Grenoble. And another important thing I need to tell you is you are very welcome to ask questions to the speakers by using the Q&A box that you will find somewhere at the bottom of your Zoom window. We strongly invite you to raise your questions during the talk, not to wait till the end of the talk, because you can view the questions asked by all other people and upvote questions so that they will float on the top of the pile, and the ones that that are most urgent then will be answered in priority. Without any further delay, I would like to introduce the speaker. Today's speaker, this is KIRILL Lomachenko. KIRILL studied at Rostov-on-the-Don and at Technical University in Munich. And then he studied at University of Torino. And he received his PhD in chemistry in 2016, jointly from University of Torino and University of Rostov. And in 2017, he joined the ESRF, where he's now a staff scientist on BEAMLINES ID24 and BM23. And the title of his talk today is X-ray absorption spectroscopy for solving chemical problems. Please, KIRILL, we're looking forward to hearing your talk.
Thank you very much, Patrick, for the nice introduction. Welcome, everybody. Thank you for being here so numerous. So indeed, I'm gonna talk today about X-ray absorption spectroscopy applied to chemistry. And the goal of this talk would be to illustrate when this method can be useful for chemical studies and what kind of chemical questions it can answer. So speaking about chemical questions, very often when we deal with some new compounds, new catalysts, and new batteries, in the end we end up with a pretty standard bunch of questions that are essential for understanding the properties of the materials. Such questions are: what are the oxidation state? of species of interest, the bond distances, coordination numbers, what is the local symmetry of particular atomic species in the compound. And of course, we are not interested in answers to these questions at 0K in vacuum for some dummy samples that's really only distantly resemble the actual ones just because they are better suited for a particular technique. No, we want this information for real world samples for our actual catalyst or battery or whatever. We want the sample to be measured in realistic conditions, in situ or operando. We want the time resolution to correspond to actual process that we're going to study. And very often we need element selectivity, so we want to have a look at the particular atomic species present in the sample. And answers to these questions under these constraints very often can be provided by X-ray absorption spectroscopy. So the idea of the essence of the method is analyzing the dependence of X-ray absorption coefficient on the energy of incident X-rays. So usually this dependence is pretty smooth, but in some particular regions, you can have a very sharp steps, sharp jumps that we call absorption edges. They appear when the energy of incoming X-rays exceeds the binding energy of electrons at particular atomic levels, core levels of particular atomic species present in the sample. And that's what makes the method element selective. So by tuning incident energy, by choosing the absorption edge, you choose which species, which atomic species, which element to look at. So due to the different physics behind and different analysis methods, the X-ray absorption spectra are divided in two parts. So one part that is one region that is closer to X-ray absorption edge is called X-ray absorption near edge structure, which is basically a reflection of density of unoccupied states of localized at particular atomic species defined by the edge that we choose. And it contains information about local geometry and the oxidation state of this species. The other part, which is further away from the absorption edge, is called extended X-ray absorption fine structure, which is basically an interference pattern that is created due to the interaction of the photoelectron wave outgoing from the absorbing atom with the same wave backscattered from the neighbors. And when this signal is Fourier transformed, we get something that is similar to radial distribution function. It's not exactly a radial distribution function, but still it's pretty similar, and it contains information about bond distances, coordination numbers, and disorder. To recapitulate, the main properties of XAS is that this method is element selective, so it probes only the species of selective elements, copper or platinum or iron, whatever you choose. Then it's also averaging, so it probes all the species of selected elements. So if you have several in equivalent positions, your resulting signal will be a linear combination of the signals coming from these in equivalent positions. And in the end, why it is useful? Well, because it contains a combined electronic and structural information about the particular species. To illustrate this, just an example of three different aqueous complexes of copper that have copper with a different oxidation state, different number of ligands, and different average interatomic distance between copper and ligands. So you can see that the XANES spectra of these three compounds are very different, and each of the spectra contains features that are typical for a particular geometry. So, and oxidation state. So that already gives an idea that XANES can be used as a fingerprinting method. In EXAFS, you can also see that the changes in coordination numbers and bond distances in these compounds are very well reflected by the relative intensities of the maxima and their relative positions. Okay, so how does it apply in practice? So let's start with some examples with, let's say, increasing the degree of complexity. So first, very simple example, we said that XANES can be used as a fingerprinting method. So we synthesize the compound metal organic framework that contains cerium. And our question is, what is the oxidation state of cerium in this compound? And what happens with this oxidation state when we desolvate the compound? So we remove the solvent from the pores. To answer this very common chemical question, we have to measure two reference spectra of cerium-3 and cerium-4 compounds, cerium oxide and cerium nitrate, and then measure the spectra of our metal organic framework in fully solvated and desolvated states. When we do it, we see at once that the oxidation state of cerium in our MOF is cerium-3 because it looks very similar to the reference spectrum of cerium-3 and not at all like the spectrum of cerium-4. So like this, X-ray absorption spectroscopy can answer this question. Another example is with palladium nanoparticles. So when we expose them to hydrogen, we form palladium hydride. When we expose them to acetylene, we form palladium carbide. But what happens if we expose them to a mixture of these gases at particular relative concentrations at particular temperature? Well, to answer this question, we have to measure our reference spectra, the spectra of nanoparticles in pure hydrogen and pure acetylene, to get an idea about how the spectra of palladium hydride and palladium carbide look like. Here you see them together with the difference spectra with respect to palladium nanoparticles in vacuum. And then we measure the spectra in our mixture, and we see that this resultant spectra look very much like the spectra of palladium hydride and not at all like those of palladium carbide. So we can conclude that we have in this mixture, we have a palladium hydride. So if we can use XANES as fingerprint, and we know that in our samples there are several equivalent states of particular atomic species, like copper, in this is the following example, we can in principle, knowing the spectra of the pure components, measuring them beforehand, we can determine the concentration of these components, so the relative weights of these components at each particular moment of time, at each particular step of our reaction, for example. In this example, we know that in our sample, there are only 3 different copper species, hydrated copper, and copper coordinated to the framework of mordenite zeolite. So here we study the mordenite zeolite, that is a promising material for methane to methanol conversion. So we have hydrated copper 2, framework coordinated copper 2, and framework coordinated copper 1. Using these 3 reference spectra, we can use a linear combination, perform linear combination analysis and determine the relative abundance of each of these species in our experimental spectrum of our real sample. You see that it works pretty well, so the agreement is quite nice if the reference compounds are selected correctly. And the good thing is that you can do this job for every step of reaction, for example, that you study, and you can get the evolution of concentration of each particular species with time, as a function of time, as a function of temperature, and as a function of atmosphere, like a gas composition in this case, right? Of course, to do this, you need to know what the reference compounds are, so which species are present. So this is quite a serious limitation. There are methods that allow to get some information even without knowing the exact the spectra of the reference compound. So you can deduce their number by principal component analysis, and you can deduce their shape using multivariate curve resolution. To illustrate this, here it is an example on another copper zeolite, copper chabazite, and 4 sequences of activation of 2 different compounds, 2 different copper chabazite were measured in different atmospheres. So here we heat them from a room temperature to 500 degrees. And when we analyze all the spectra together, it appears that this whole sequence of all the spectra can be decomposed into 5 different principal components. And the spectra of these components are shown here. And in order, and now there's a big task is to associate the spectra that are mathematical, basically mathematical curves with the real species. And this can be done if you have the prior knowledge of the system that we had, luckily. So we could, without a problem, attribute each spectrum to a particular copper state. And once this is done, you can have a concentration profile for each of the species for your reaction. And this helps you to correlate the structure or the relative composition of these compounds with their properties. Another good thing about XANES is that XANES spectra can be calculated. So if you have a model deduced from a theory, from a DFT calculation, from electrodynamics, or from some other structural sensitive method like X-ray diffraction, you can calculate XANES spectra, and you can determine the structural parameters, local structural parameters, comparing the experimental spectrum with the theoretical spectrum. It can be done using several codes. Probably the most popular and the powerful ones are FEF, developed in Seattle by a group of John Rare, and BEAMLINES, developed here in Grenoble by Yves Joly, and upgraded recently by a group of Professor Soldatov and Rostov. Okay, coming to EXAFS, the huge advantage of EXAFS compared to XANES is that the EXAFS has an analytical formula that can describe the signal, the EXAFS signal, more or less well. This formula actually describes this oscillatory pattern, and you can distinguish 2 types of terms here. Those in blue that are usually calculated, most often they're calculated by FEF, and those in orange that are usually fitted. And those in orange, they are actually those that we are interested in when we analyze the structure of our material. From chemical point of view, what we need to know the bond distances and coordination numbers. So here we have them in this formula. So by doing EXAFS fitting and minimizing the discrepancy between the fitted curve and the experiment, we can find the values of these parameters that correspond to our material. So a simple illustration of this is UIO 67 MOF functionalized with palladium. So it's a cubic MOF with the majority of linkers that are biphenyls, but some of them are substituted with bipyridine, with palladium grafted to it, coordinated also with 2 fluorine ions. The question here was whether the structure of this linker molecule with palladium, whether it is maintained after the synthesis of MOF has been done. So the linker the synthesis was done pre-making the linker. So the linker was ready before the synthesis. And then we synthesize the MOF. And we want to know whether the linker molecule is still intact, whether the local environment of palladium is still the same. What we do, we measure EXAFS at palladium KH for the linker and for the MOF. And we see it once at first that we see is that the spectrum of the MOF, the EXAFS spectrum of the MOF is exactly the same as the spectrum of palladium linker. And when we analyze the data, we do the EXAFS fitting, we see that the signal can be very well reproduced by two contributions, palladium nitrogen and palladium chlorine, with the coordination numbers and bond distances that can be very precisely determined by EXAFS, so we get precise values of this coordinate of bond distances and coordination numbers. EXAFS can be used also for a little bit more sophisticated analysis. For example, this one related to the UIO 66 material. It's a cubic MOF again that has in its original form, it has its zirconium cornerstones. But zirconium and these cornerstones can be partially or completely exchanged with cerium. And a series of these materials with different cerium content was synthesized by a group of Professor Stock in the University of Kiel. And what they saw is that the temperature dependence, the temperature stability of these materials, depending on the cerium content, is not very straightforward. So it was not really clear why it looks like this. And even more simple question about whether we can have zirconium and cerium in the same cornerstone couldn't be answered from prior knowledge. In other words, whether we have something like this, where zirconium and cerium cornerstones in bimetallic compounds are segregated, or we have something like this, where zirconium and cerium can be present in the same cornerstone in the material. So these questions could be answered after doing a rather sophisticated EXAFS analysis. And EXAFS was particularly helpful because with zirconium KH and cerium KH EXAFS, you are very sensitive to this metal-metal interaction. So you can determine the metal-metal distances, and you can distinguish easily between cerium and zirconium neighbors. So what was done is a measurement at cerium KH and zirconium KH for a series of materials with different cerium content from 10% to 84%, and also the pure compounds. And just looking at the spectra, actually it's a zoom on the metal-metal part, the peak that is responsible for metal-metal interaction. Just looking at the spectra already, it's very clear that we don't have a segregation of the cornerstones, because if we had only the pure cornerstones, the spectra shouldn't have varied at different cerium content. Just because for each particular cerium or zirconium atom, the situation wouldn't change, the local environment wouldn't change at all as a function of cerium content. Instead, it's clear that we have a mixture of cerium and zirconium in the cornerstones. And again, qualitatively looking at the data, where at zirconium KH we have a very high intensity for low loadings, and the intensity that does not change quite a lot for materials with a loading above 20%. And looking at cerium KH, where we have a minimum of intensity for intermediate loading materials, it's plausible to suggest that we have the following picture, that we have only the three types, predominantly on the three types of the cornerstones in the materials: so pure cerium, pure zirconium, and cerium zirconium 5. And the latter should form preferentially at all the serum contents, while the other two should complement the mixed metal cornerstone to reach the desired global serum content. So this is a qualitative hypothesis that corresponds pretty much to what we see, but the good thing is that we can do an EXAFS fitting at the two edges for 5 different compounds at the same time, for 6 different compounds at the same time. So 10 different spectra, and we find that the agreement, the quantitative agreement of this model with our hypothesis is very good under the realistic physical constraints. So, of course, the XAS method is not methods, they are not dedicated, they are not exclusive only for catalysis related applications that I show. So, for example, in electrochemistry, XAS can be equally useful. So in these 2 examples, you see that it's very, it can be, well, it's possible to follow the discharge of the battery, for example, and the evolution of the local environment of particular atomic species in the cathode or anode of the battery, like vanadium in the case on the left and tin in the case of the right. So we can do the in situ measurements, but of course the electrochemical cell and also the catalytic cell should be compatible with the limitations of the technique. So the geometry basically has to be compatible. Also the thickness of the sample should be compatible, and the amount of the species of interest should be compatible with the XAS measurement. But the tolerance is pretty large, so these measurements are pretty much doable. Another important strength of the XAS methods is that they can be rather easily combined with other techniques. And when you use several techniques at the same time, well, you look at the same problem from different angles, and it makes your results much more reliable. So in particular, at BM23 beamline at ESRF have a combined XAS drifts setup coupled also with the mass spectrometry, which allows you to get basically mass spectra, XAS spectra, and infrared spectra from the same sample at the same time at controlled temperature and at controlled gas composition. And this approach is actually very fruitful, as illustrated, for example, by this study made by the group led by Professor Elena Groppo from Turin. And here the focus was at the structure of interaction of platinum nanoparticles with hydrogen, so the formation of platinum hydride. And infrared was used to monitor the hydrides themselves, while the XAS was used to probe the structure of platinum nanoparticles. And these 2 methods were very much complementary, and they allowed to determine to shed light on the evolution of platinum hydrides as a function of hydrogen concentration in the gas feed. So the bottom line, when you should think about XAS, well, basically, to cut it short, when other methods that may provide the necessary results under certain conditions, when these methods do not work. So, for example, when you need element selective information on local geometry, electronic structure of particular species, so you don't want to use volume, you don't want to use methods that, for example, are very much relying on a long range order, so because you want information of local geometry. So when your sample is not crystalline, or it may even not be a solid, so it can be liquid or some amorphous sample. So X-ray diffraction, for example, will not be as precise as for perfect single crystals. When you have your species of interest that are disordered in the porous crystalline matrix, like in most zeolites, so these materials are very good crystals, but the thing that does the catalysis basically are isolated metal ions inside the pores. And it's not very straightforward to track them with methods that are not element selective. And also you can use these methods when the species of interest are too small to diffract. So XAS can be a method of choice. And the last thing that is common for most of X-ray techniques, hard X-ray techniques, that they are very powerful when we need in situ operandi measurements, because hard X-rays have very high penetrative power. So XAS can be measured, XAS spectra can be measured in many beamlines at ESRF. Many of these beamlines, they add some particular flavor to XAS, so they specialize in some particular aspects like magnetic measurements or nano beam measurements and so on. So I represent BM23 and ID24 beamlines, so I will talk a little bit in detail about these beamlines. So they are dedicated to chemistry and extreme conditions studies. So we have two global major activities: chemistry, all sorts of chemistry, catalysis, electrochemistry, photochemistry, and so on, in rather mild conditions relative for chemical studies. And we can control the gas atmosphere. We can use complementary techniques that allow us to get a very broad range of information about the samples. And the extreme condition part is mostly devoted to condensed matter physics, to geology, to magnetism. And here the conditions are really extreme. So very high pressures, very high temperatures, or very low temperatures, high magnetic fields, laser shocks, and so on. So things that are not directly related to chemistry, but also very, very, very exciting. And the time resolution available at these two beamlines is the range is very broad. It goes from minutes to picoseconds. Talking a little bit more in detail about the beamlines, BM23 is a general purpose XAS beamline that has an excellent stability, broad energy range, and possibility to use a microbeam down to 4 microns, which is not very often used for chemistry, so it's much more important for physics and chemistry, not so often, but can be used as well. So main applications in chemistry of this beamline are the ex situ and in situ operandi studies, but relatively slow ones, so relatively slow chemistry. With a time scale of minutes or tens of minutes, and also the industrial experiments. The other beamline, ID24 DCM, is a high brilliance XAS beamline that is currently being built in the place of one of the previous hatches of energy dispersive ID24. This beamline will feature very high flux thanks to the undulator source. We'll have a scanning monochromator developed by ESRF and a possibility to focus down to 1 by 1 micron beam. And the goal is to reach the acquisition time of for 1 EXAFS, 1 second per 1 EXAFS. So every second we can measure a high quality EXAFS that can be analyzed by itself without further averaging. So to get a good EXAFS spectrum every second, and we are pretty confident that we can reach this goal. So this beamline will be used for fast chemistry in situ and operandi. For multi-technique studies, we will have possibilities to do XRD, XRF, X-ray emission, infrared, mass spectrometry there. So it will be a very versatile tool for chemical studies. In terms of sample environment, we are very well equipped for chemical studies. We have a lot of our own equipment, and the equipment also provided by ESRF sample environment labs that is extremely helpful, and they have a lot of different equipment available for users, so use it as the users, being users. Now Beamline, we have, I guess, mixing setup, ovens, UV lamp, as I said before, infrared spectrometer. So a lot of different equipment that can satisfy many chemical needs for in situ and operandi chemistry studies. And all this in combination with the reliability of the beamline and high quality beam provided by the ESRF machine, which will hopefully become even better with the current ESRF EBS upgrades, that is very important for us. Well, and thanks of course to you, to all of you, to our users, we managed to produce pretty good publications that we are very happy about, and we thank you for actively contributing to it. So just in the end, recapitulation about the ways how you can get a beam time, because in the end, as a users, you may be interested in how to get beam time and to get access to all this fantastic equipment. So there are three main ways, basically: the peer reviewed proposals, 2 calls per year, and the good thing about it is that the expenses are covered if your institution comes from the ESRF member states. The next deadline is March 2021, because the previous call has just ended. Deadline was September 10, but the next one is in March 2021. So have a look at the ESRF website in order not to miss the date. It should be like by the 1st of March, the first days of March. Then there is a possibility of commercial beam time. If you are interested, please contact Business Development Office of ESRF. So here the access is much faster, but and there is no obligation to publish the results. So you do what you want with the data you collect. You can use it for proprietary research, for industrial research, but of course it comes at the expense of the fee. Yeah, and the third possibility is a collaboration with the beamline scientists. So you can also contact the beamline scientists at the beamlines that you are interested in and suggest to collaborate. Finally, many thanks to all the wonderful people that contributed to the studies that were mentioned in this talk. People from all over the world that I'm very fortunate to work with. And last but not least, thank you all for your attention. Thank you all for being here and being so numerous.
Thank you very much, Kirill, for the very nice presentation. It was very exciting. And indeed, we have a very large response, many participants and many questions. So are you ready to take some questions?
Yes, I am. Okay. With pleasure.
So we have a number of questions concerning the possibilities of using the various techniques. And in particular, we have a question by Vasily Lebedev. Could you please let us know about the possibilities of combined in situ powder X-ray diffraction and X-ray absorption spectroscopy at ESRF?
Yes. Well, to cut it short, there are such possibilities. This is very powerful combinations because the two techniques are very complementary to each other. Of course, each technique has constraints, and if you apply both of techniques at the same time, you have to satisfy both constraints. If it's possible for your samples, then you're fine. You can do combined XAS and XRD studies and different beamlines. Like you can do it at BM23, you can do it at BM31, the Swiss Norwegian beamline. You will be able to do it at ID24 DCM. These are the beamlines that can, and probably other beamlines, some other XAS beamlines as well. The constraints I was talking about is that for XAS, you should optimize the thickness of the sample. So the sample should be of particular thickness that can be calculated depending on the concentrate, on the elemental composition. And this sometimes may not be very well compatible with XRD studies. Another thing that to measure a good XRD, very good XRD, you should use a relatively thin capillary. And this thin capillary, again, it may be not compatible with XAS studies if it's too thin and if you cannot have enough contrast for XAS measurement. But for many, many cases, it is possible to do both, to apply both techniques. And please contact the beamline scientist at the corresponding beamlines for your particular, to discuss your particular scientific case, because it's pretty easy to determine beforehand whether this experiment is feasible or not.
Kirill, we have further questions along the same lines, and we have a question, for example, from Roberto Tazzano, which is it possible to do XAS on samples while heating, for example, from room temperature to 500 Celsius for a spectra at different temperatures?
Yes, absolutely. It is, well, it is possible. Technically, it is possible, and that's what we do routinely at BM23, for example, and at many other beamlines. It is possible if you have a dedicated oven that allows to heat your sample. If you have it, and I mean, we have it, so if you apply for BEAMTIME in ESRF, you can get access to it, no problem with it. You can absolutely make an in situ measurement heating your sample from room temperature, from whatever temperature, to 500 degree or 1000 degree. It's the only limitation that you have here is your cell. So if the cell allows it, you can do it for XAS, there is no problem. Of course, at high temperature, you can have a high contribution due to high thermal contribution to EXAFS, which makes basically your EXAFS oscillations less intense. So it dampens, the temperature dampens the amplitude of the oscillations. So at very high temperatures, you'll be less, you'll have a data of lower quality, but 500 degrees is absolutely doable. That's what we do routinely, so it's not a problem at all.
Thank you. There is one question which has been voted by many people, again from Vasily Lebedev, and which is the following. Let's assume there are two oxidation states of atoms in interest in the specimen, cesium 3 plus cesium 4 plus. Could you please tell a bit more how it will impact the EXAFS part of the spectrum and whether one should use different atom models in the FEF model?
Yeah, this is a very good question. Yeah, in principle, if you have species with a very different oxidation states that lead to a very pronounced shifts in the X-ray absorption edge, that you might want to try different independent E0 during the EXAFS fitting. Yeah, but E0 is most often fitted. Well, it's basically always fitted. So it's not. It does not come. I mean, it's not a part of your. It's not something that you calculate. So usually you fit it. And the question here is basically whether you use the same E0 for the different species or you use a different one. So most often you use the same, but if the species are such that the difference in the energy of their absorption edges is not negligible, so it's quite large, several electron volts, you'd better try fitting it with different E0s.
Thank you. Then we have a question from Dmitry Doronkin. Did the BM23 flux increase after the EBS upgrade, and how much? Do you need to introduce new protocols to fight the beam damage now? Okay,
Dmitry, thank you for this question. Yes, we foresee the flux increase at BM23. That will not be very dramatic, so it will be around a factor of 2. So we will have a little bit more photons. But since we don't use usually for chemistry experiment, well, we take only very narrow band of the radiations that comes from a bending magnet, now from the wiggler, so we don't focus the whole fan. The flux in general is not very high, so it's not an undulator beamline, and the flux is lower at compared to some other bending magnet beamlines. So even when it is increased by a factor of 2, we do not foresee any significant radiation damage if you work in an unfocused mode like you do for chemistry most often. So we don't foresee significant problem with the radiation damage unless your samples are super sensitive, and I guess yours aren't. However, this will be a big problem at ID24 DCM and a big issue, and we are ready to face this issue. So we'll have to be very careful with the attenuators of the beam. So we'll have to, for each particular experiment, depending on the nature of the samples, we'll have to attenuate the beam to, of course, as little as possible, but to an extent that the beam does not alter our samples and does not alter the chemistry that we are studying, which is even more tricky than not to hurt the samples themselves.
Thank you. Next question is from Marie-Paul Basset. Were some of your samples in solution? Which beamlines did you use? You answered already. Could you adjust the size of the beam? What is the smallest size of the beam?
So from XAS point of view, XAS does not care whether the samples are in solution or in solid or even in gas. So the limiting factor is the concentration of the absorbing species. So it's absolutely no problem if you want to measure in solution. Measuring in solution is not a problem at all if the concentration of the absorbing species is compatible with the measurement, with the data qualities that you want to get. Actually, liquids are very nice samples for us because the very good XAS data quality can be obtained only for quite homogeneous samples. So the higher is the degree of homogeneity of the sample, the better is the data quality. Liquids are perfectly homogeneous, right? Most often, if it's like a true solution. It's much more homogeneous than a powder in a capillary, for example. So usually you can get a very good data from liquids if the concentration allows it. Then there was a question about the beam size, I guess. So at BM23, we have 4x4 micron for focused operation and something like 0.5 millimeter in vertical by up to 10 millimeter in horizontal for unfocused operation. But most often we use something like 0.5 by 3 millimeters at BM23. In ID24, it will be something like 1 by 1 millimeter in unfocused mode and 1 by 1 micron in a focused mode. The question about FAME, unfortunately, I never measured at FAME, so I cannot tell about the beam size. You can look at the ESRF website. There is a page, it's called Find the Beamline, and there you can see the beam size that they offer, and you can also contact the beamline scientist. And I think there was another question in this long one that I do not remember, and I cannot find it anymore. So, yeah.
Thank you. Now a question by Thomas.
Sorry, Patrick. Sorry, I found it. The question was, could you adjust the size of the beam? Yes, you could. You can adjust the size of the beam within certain limits, but you can.
Yeah. So yeah. Thanks. So the next question is by Thomas, and it says, in the absorption spectroscopy at ESRF, is it fit for XANES and EXAFS at for measurements in metalloenzyme, say 1 iron atom per 1,000 atoms in the sample? And iron is the interesting element. So it's about the sensitivity of the methods.
Okay, I see the point. So it's
if the probe is diluted 1 to 100,000.
Yeah, first of all, it is important. I mean, you wrote metal enzyme, so most probably the rest of the atoms are the light atoms, so yes. Carbons, oxygens, nitrogens, which is quite good. Because if you had a matrix of, I don't know, of lead atoms, and you had an iron per 100,000 leads, then there is no way. For the light atom matrix, 10 ppm,
the organic stuff, yes,
right? You can get something. I think you can get something. You will have to use a fluorescence mode. So there are different ways of measuring XAS. You can measure in transmission, or you can measure in fluorescence. In transmission, I'm sure you will not get anything because you have too little iron. But for fluorescence, I think that there is a chance to get XANES for sure. And if you, depending on how much time you are ready to invest into it, if you measure for a long time, you can get also some reasonable quality EXAFS. But again, it depends on your scientific question. So if you want to determine the iron oxidation state, for example, then XANES would be enough, and it's surely perfectly feasible. If you want to determine some very, very fine details of local structure of iron 5 angstrom away from iron atom, then no. So it's depends. Yeah. It depends on the composition and on the questions that you want to answer. The general answer that it's most probably feasible.
Okay, thank you. Then we have a question by Ripan Biswas, which is, what are the possibilities of modeling EXAFS XANES data for glasses for investigating local structures? Is there any particular software available for application to glasses like Athena?
Yes. But first of all, modeling of XANES and EXAFS and EXAFS, XANES and EXAFS has nothing to do with Athena. So Athena is not software for modeling. It is for data reduction and data analysis. So the data analysis in Athena can be performed for any kind of hard X-ray spectra, XANES and EXAFS, no matter the sample, if it's a glass or crystal or liquid, no problem. For modeling of XANES and XANES, you can use FEF or FDMNES to calculate the spectra. If you have many equivalent positions, you might have to average the different contributions. But there are also programs that allow you to do the EXAFS modeling for amorphous material where you don't have a very, very defined coordination shells. So it is possible.
Sorry, there was a question elsewhere. Let me check what is question that was not answered. Yes.
Oh, there are like many.
There are many of them.
Oh, may I answer one?
Yes.
There is Mike Wiedenmeyer that asked me about the possibility to use a combined drifts XAS, drifts MS setup and the information about its availability. I want to answer this because actually now we're working quite a lot in on this setup, on improving it. And yes, this setup is available. Data quality is good. It's available for users. So please don't hesitate to apply for it, to use it. And yeah, everything works very nicely. So if you need some details, please don't hesitate to contact me directly.
Yes. A question from Nina John. By looking at oxidation states changes using X-ray absorption spectroscopy, is it necessary that we compare with standard samples of similar oxidation states?
It depends again what you want to do, what information you want to obtain. Measuring standard samples, reference compounds, is a very good practice because it may help you to understand what happens with your actual sample. So you can compare, you can get a lot of information by comparing the spectra of your sample with the spectra of reference compounds, standard samples. Ideally, the standard samples should be measured in the same conditions than your actual sample. So at the same beamline, the same acquisition mode, it would be, it's the best way. So usually when you come to make an XAS experiment, it is highly recommended that you bring as many reference compounds, so standard samples, as possible, because then it will facilitate, it might facilitate the analysis of your data for you.
One question now from Matthijs van Swansen. What is the limiting factor in decreasing the acquisition rate? I suspect it was meant increasing the acquisition rate. And what tricks do you apply to get it down to 1 spectrum per second?
So there are different factors. The one is the flux. So if you want to measure very fast, then you might not have enough photons to get a measurement that is fast. So maybe if you, for example, if you have a, I don't know, a laboratory source, an X-ray tube, you have very low flux, so you cannot measure in 1 second. You cannot even measure in 1 minute, so you have to accumulate further. So in ID24 DCM, we're going to have an undulator source, a lot of photons, and this will not be a problem. We will not be limited by flux. Another thing is mechanics of the monochromator, for example. So there are different ways of acquiring the XAS spectra. The most simple one, the original one, is a step-by-step scan. So you measure one point, then you move to another one. You acquire, you move. You acquire, you move. So this may give you a lot of stability. So you can be stable, very stable in this mode. So your beam position will be very stable on the sample. That is good. But of course, this measurement will be rather slow because you will need time to go from one point to another. So that time will be rather large. Another possibility is when the monochromator is moving continuously and you are integrating continuously. This is how it will be done in the ID24 DCM. So it will be faster in this sense because we will not have a dead time moving from one point to another. The monochromator will move continuously. If you want to go even faster, there are possibilities to use so-called oscillating monochromator that can move with a frequency that is very high, up to, I don't know what is the current record, but something like 50 Hertz is doable. And this, we don't have such a monochromator. There are advantages and disadvantages of such setup. And yeah, but it's true that it's for, if the sample allows it, and if the amount of photons that come from a source allow you to measure fast, with this monochromator, you can measure very fast. You can measure 10 spectra per second or even more. But under some very important constraints that have to be taken into account.
Thank you. A question now from Silvia Morante.
Yeah.
Reason why the lowest energy available is just above the calcium edge that should be of great interest in biology?
The lowest energy available is defined by the characteristics of the X-ray source. So as you know, ESRF is a high energy machine, so it's a 6 GeV source. And the critical energy of ESRF is around 20 kilo electron volt. So the lower we go in energy, the fewer photons we have in principle. At all, I mean, the fewer photons of low energy are emitted from our X-ray sources. And the second problem is that calcium, I don't remember by heart the energy, but it should be already in entering towards the soft X-rays. And soft X-rays applications, they require different instrumentation. So you should already work in vacuum. You should, your monochromator should allow you to go to such high angles, or if it's even low energy, you have to use completely different type of monochromator. So, I mean, we cannot do everything. There are beamlines at ESRF that can do calcium KH. I don't remember by heart the energy, so I'm sorry for not being able to provide more detailed answer. But it's related with the instrumentation constraints. It's not that we don't like calcium. It's instrumentation related constraints. That the tools that there is no tools that can do everything. But it is also for low energy measurements like soft X-rays. It's possible that there will be much more possibilities at the lower energy machines, lower energy synchrotrons for low energy measurements.
Thank you. Well, the continuous flow of questions is a very good sign of the strong interest generated by your presentation, but we should soon wrap up this. And so I will come to a last question.
Sorry, Patrick. Yeah, Sylvia, thank you very much, Sylvia, for writing the energy. It's 4K for calcium. Well, yeah, 4K, unfortunately, is right. Is just a little bit below from what we have, the possibilities that we have in BM23. We just, yeah, with the current mono, I think we cannot reach it. And with the mono, with the mirrors, we cannot reach it, even if we put everything in vacuum. But in other beamlines in ESRF, you can measure this. You can measure calcium KH without a problem for sure.
Yes. So, well, there were a number of people asking whether the slides would be available for people. I remind everyone that the talk will be available on YouTube, and hopefully maybe the slides could, PDF of the slides could be available from the YouTube page as well, but we will check that with Kirill. And so the last question I would convey is from Ripan Biswas. Which technique is more helpful for extracting short-range structural information, XANES or atomic pair distribution function, or a combination of them?
Oh, if it's formulated like this, then of course it's a combination of a combination is always nice because you can have different.
But are there specific limits of one or the other?
Local or local or short range structural XANES or atomic pair distribution function is a combination. Well, it depends. I mean, it depends also on the sample, on the problem. Because PDF is, it's a very powerful technique, but it lacks the degree of element sensitivity that XANES has. So depending on your sample, if your sample contains, I don't know, 0.1% of the species that you are interested in, like in the question before, there was a question about the proteins or metalloenzymes with iron that is 1 out of 100,000 atoms, it's iron. If you do a PDF of this compound, you will not see iron at all. So if you do XANES, you will see only iron and its local environment. So everything depends on the sample.
Thank you.
Both techniques are very powerful in general.
Okay, so with this, I think we shall close the discussion. Very big thank you to Kirill for the wonderful presentation. Very big thank you to all the participants. We had a very numerous audience and many questions. And I invite everyone to join us again in a week from now for the colloquium on exoplanets, and then for the further webinars of this series.
Just if I may, there are like 10
Yes.
questions that are not answered. I mean, if you feel that we didn't discuss something or you need some more information, please don't hesitate to drop me a line to lomachenko@esrf.fr. So I'll be happy to discuss your problem, your scientific case.
The phone book is on the ESRF webpage. You can find the emails of all people you want to ask questions about.
It's not only me. Yeah, you can.
Questions. We are all very happy to receive those questions. And
yes. Yeah, so I'm really sorry that we cannot answer all the questions live, but I will be happy to answer them privately.
With this, have a nice day, everybody.
Yeah.
And
thank you very much.
On Zoom or YouTube. Bye.
Thank you. Bye.